Hello, and welcome to the Unit 7 review for AP Chemistry. So, Unit 7 looks at chemical equilibrium, all right, the enduring understandings. Some reactions can occur in both forward and reverse directions, sometimes proceeding in each direction simultaneously. That leads us to the idea of chemical equilibrium. A system at equilibrium depends on the relationships between concentrations, partial pressures of chemical species, and equilibrium constant K. The systems at equilibrium respond to external stresses to offset the effect of the stress. That is Le Chatelier's principle. And then the dissolution of a salt is a reversible process that can be influenced by environmental factors such as pH or other dissolved ions, so solubility. All right, so some reactions can occur in both forward and reverse directions, sometimes proceeding in each direction simultaneously. All right, in this example, we have two flasks of water, both are stopped. All right, what will begin to happen is water molecules in the liquid phase will be able to evaporate. They'll go into the gas phase. And some of those gas molecules, when they come near the surface of the water, will recondense. So this is a forward and a reverse process, the evaporation and the condensation, and they're happening simultaneously, right? So it's not just the fact that it's something that's reversible, liquid to gas, and then gas back to liquid. It's that they're also happening simultaneously. All right. Another common example is a salt in a solution. All right. Some of that salt may be solid or precipitate. All right. For here we have Ma. The M is the metal, right? A cation. The A is the anion. And so some of those ions are dissolving into the solution, and then some of them are going back and precipitating. They're reforming the solid. So it is a forward process dissolving, a reverse process precipitating, and they're happening simultaneously in this solution. All right. The transfer of protons in acid-base reactions. The protons are the hydrogens, right? So we can see the hydrogen from the HNO2 joining the water, forming the H3O and the NO. All right, now acids and bases are unit 8, that is correct, but it's a big topic because they are often equilibrium situations, which is why it shows up here. And the transfer of electrons in redox reactions. All right, the Fe3 plus ion can gain an electron and become Fe2 plus, so it can be reduced. And then the Fe2 plus can lose an electron and become Fe3 plus, so it can go back and forth from being reduced and oxidized. All right, so it can go back and forth, and if these two processes are happening simultaneously, that would be a chemical equilibrium. All right, so it's important with chemical equilibrium. We want to think in two scales, microscopically and macroscopically. Okay, microscopic, that's our particle diagram view. We're thinking about the individual atoms, the individual molecules. And chemical equilibrium microscopically is dynamic. All right, we are seeing change happening again and again. The reactions are going back and forth. All right, so we have this A plus B forming C plus D. They're going back and forth several times. All right, but macroscopically, chemical equilibrium is what we will say static. All right, there will be no observable changes occurring in the system at the macroscopic level that we see. All right, it'll look like nothing's happening. A lot of colored solutions have some type of equilibrium going on, especially with the oxidation states. All right, now we don't see reactants and products going back and forth. We just see it staying as one color, right? Macroscopically, equilibrium is, we'll say static, microscopically dynamic. All right, so again, no observable changes occur in the system that we would observe. All right, so the equilibrium state is dynamic. It's going back and forth. So here's an example of two ants moving rocks between two piles. All right, the size of the piles will not change because for every one rock that we lose, we gain one, right? It's like an even Stevens here. So it's gonna have to focus on the rates. Equilibrium is based on the rates being the same. All right, so if the ant removes one rock and brings it to the products pile, but the ant up top brings a product rock to the reactants pile, all right, the rate that they change stays the same, and so the size of the piles stay the same. So we don't observe any change, but dynamically, these ants just keep working. All right. The example here is a container of bromine. All right. If you had liquid bromine in a flask, some of it is going to boil. It's going to go into the liquid phase, and some of it's going to condense. All right. It's just like the water example from before. It's going to be happening back and forth, and that's a very dynamic change that it constantly is occurring. All right. And so the idea is it's occurring so much that the rate stays the same, and so the concentrations of each stay the same. All right. Now, graphs will be important. So we've seen graphs in Unit 5 with the reaction rates. So the concentration of A is decreasing, so we know A is the reactant and B is the product here. All right, but after about 2 seconds, we see them leveling off. If the concentrations plateau, that is a sign we have reached that equilibrium. All right, so that would be for concentration. All right, and they don't have to cross paths. So here we see the reactant decrease, the product increase. It's totally fine that we still have more reactants than products. They've plateaued, so that's how we know we're at equilibrium. All right, they can crisscross. That's totally fine. We would end up with more products here, less reactants. All right. Now we can also look at the partial pressures. That's another thing that we can graph versus time. So here we see A, B, and C are all the same. There's some change. We see A take an uptick, right? And then everything kind of levels off. So once they level off again, we have reached that equilibrium. This will kind of have to do with our stresses later in the video. All right. But the important thing, when we want to see a graph where the two pieces meet, is when it's a graph of rate versus time. We want the forward rate and the backwards rate to equal each other. So if it's a graph of rate versus time, we want to see them equal each other. All right, it's not just that it's plateauing, it's that they are equal to each other. If one rate is faster than the other, we are not at chemical equilibrium. All right, so equal rates means we're at chemical equilibrium, and when the concentrations stop changing means we are at equilibrium. All right, we did the example in class where we moved the water back and forth. All right, if one of the rates is faster, either the forward reaction or the reverse reaction, what'll happen is as the reaction proceeds, all right, if the forward reaction is faster, the reactants will actually use themselves up and they'll slow the reaction rate down on their own, right? Because we don't have that many reactants. So we saw in this metaphor where we passed the water back and forth, the amount of water was like the metaphor for the rate. And even if you have a big cup and a small cup, eventually the amount you're pouring between the two large beakers will be the same. All right, so an equilibrium state is reached when these rates become equal. They don't start off that way necessarily. All right, and I just wanted you to think about the faucet. As it pours in, it's pouring out. The idea is that they have to be going at that same rate. All right, so I've said it like 15 times now, but the rate has to be the same. If it doesn't start out as the same, the rates, they will adjust. One of the rates will speed up, the other will slow down until they meet if it's a chemical equilibrium situation. All right, so now we need the expression K or the expression Q. They look the same. All right, so what we do is if we have an equilibrium, we write out the arrows forward and backwards, right, to show that there's the forward and the reverse reaction happening simultaneously. The concentrations of the products divided by the concentrations of the reactants is how we set up this equilibrium constant. That would be K, or for Q, it's the reaction quotient. And they get raised to the power of their coefficients. So the concentration of C, for example, raised to the power of that lowercase c. We'll see some examples. All right. Now the idea is at equilibrium, the reaction quotient is equal to the equilibrium constant. All right. So if Q is less than K, that means that we have more products. And if Q is greater than K, that means we have too many reactants. Either way, they will meet at that equilibrium. All right, so the idea is K doesn't change, at least not for a given temperature. So Q will move to meet K. All right, I think the easiest way is to draw a line graph. If Q is to the left of K, that means the reaction needs to move to the right. All right, that's the forward reaction. And if Q was greater than K, the reaction would move to the left, which would mean the reverse reaction. All right, so again, K describes a reaction at equilibrium. Every equilibrium reaction will have some K EQ, the K of the equation, that's the rate constant. It is unitless, so you don't have to worry about that. Q describes a reaction at any given time. So Q is a good way to determine if a system is at equilibrium yet or if it's heading there. All right, now we will see different versions of K. If you see it with that C, all right, Kc means that is the rate constant for concentration. We use the brackets. So for this reaction, 2SO2 gas plus O2 gas in equilibrium with 2SO3 gas, products go on top, concentration of SO3, raised to the second power because of the 2 in the balanced equation, divided by the concentration of SO2, all right, one of our reactants, raised to the power of 2. Okay, so products on top, reactants on bottom, times the concentration of O2. All right, now if we're looking at a gas, so we have another reaction here, H2 gas plus I2 gas forming 2HI gas, all right, hydrogen plus iodine, forming hydrogen iodide. We can use the partial pressures. So you would use the P with the subscript of whatever substance you're representing. So the partial pressure of HI, again, squared because of the coefficient 2 for the product. All right, products divided by reactants. So the partial pressure of H2 times the partial pressure of I2. All right. And we can relate Kp, right, the rate constant for a partial pressure, to Kc, the rate constant for concentration, with this formula. Kp equals Kc times RT raised to the delta N. All right, R is the gas law constant, 0.0821. T is the temperature in kelvins. And delta N is the change in moles of gas. You're only looking at gas for this, all right? We would only use Kp and Kc for a reaction where everything was a gas. And delta N would be the number of, moles of gas as a product minus the number of moles of gas as a reactant. If it's the same number of moles on each side, right? So let's say it was 2 moles of gas formed as reactants, forming 2 moles of gas as products. Delta N is going to be 0, right? 2 minus 2. And so anything raised to the 0th power would be 1. So that's a situation where Kp can equal Kc. These are just different ways of expressing the rate constant, though, for concentration or for partial pressure. All right, so again, here are all of our formulas. And again, if it's concentration, we want to make sure we use those brackets. And if it's partial pressure, we want to use the P with the identity of the substance as like a subscript. All right, we want to be careful with that. You don't want to use brackets if you're doing partial pressure, all right, because it's just not following the system and you want your answers to be very neat for the graders. All right, so again, here's just an example. Constant, it is products on top, reactants on bottom, and we use the coefficients come from the stoichiometric coefficients in the reaction. All right, now the reaction quotient does not include substances whose concentrations are independent of the amount. All right, what that means, we do not include anything that is a liquid, all right, so it would have that L tag, or anything that is a solid. All right, we can take the concentration of an aqueous piece, we can take the concentration of a gas, but we cannot take the concentration of a solid or a liquid. So that's why H2O liquid typically is omitted. In this example, we have our Kc equaling concentration of H2 times CO, right? Both of our products divided only by H2O. H2O is there because it's a gas. The pure carbon is omitted because it is a solid. All right, had this H2O been a liquid, it also would have been omitted, and we could just make this piece 1, so it'd be H2 times CO. All right, it is fine with omitting solids and liquids that you might not have any reactants in the rate constant. You might not have any products. If you're ever in that position, just put a 1 there, all right, as a placeholder. All right, now, equilibrium constants can be determined from experimental measurements of the concentrations or partial pressures of the reactants and products at equilibrium. All right, one of the best things that we're able to do in a lab to get an idea of this is look at the color. All right, typically when the color stops changing, that's when we know a system is at equilibrium. And based on the amounts of reactants and the amounts of products, all right, we can have an equilibrium in different positions, and so it'll have different colors. Typically, the reactant may be one color, the product another. We get really great reactions when one of those is colorless, so we can get an idea of how much we have. So here's an equilibrium that is like an orangish brown. And so as we get a lower concentration, it gets lighter. So we can make some observations just by looking at the color of the solution. All right. If we were trying to look at partial pressures, all right, we can use a gas pressure sensor. All right. So we can see if the pressure spikes up or if it decreases, and we can kind of measure that over time. All right. So typically that'll be kind of challenging in the lab because we're just going to get the total pressure, but we can get an idea of what's going on by watching partial pressures, all right, observing what is taking place. All right, now, if we get a very large value for K, all right, a large value for K means we have a lot of products and we're dividing by a small number of reactants. So in this reaction, H2 plus Br2 in equilibrium with 2HBr, right? We see it visually. We don't get a lot of the reactant in product, a lot of the reactant, excuse me. We don't get a lot of the H2 or the Br2, we see mostly products, all right? So when an equilibrium has a very large K value, it means that it's occurred essentially to completion. There is still that reverse process, but once we reform the reactants, we almost immediately reform the products. That's a very large value for K. All right, so again, large values of K, mostly products. We're talking of a K value larger than like 10 to the third. All right. Now, if we get really small values of K, and again, they're saying K less than 10 to the negative third, really small values of K means we have the opposite effect. Mostly reactants, very few products. So only in this range from they're saying K of about 10 to the negative third to 10 to the third do we start to get significant amounts of both. All right, so some equilibriums barely proceed. These are the really small Ks, and those are said to favor the reactants, or the reverse reaction is favored. All right, and when K is very large, we say that this is an equilibrium that favors the products, or the forward reaction is favored. All right, so now we can manipulate K. The rate constant can be changed around. So what if we were to just rewrite the equation backwards? All right, so if instead of saying A plus B in equilibrium with C plus D, right, where our K would be our normal products divided by reactants, if we were to flip the reaction around, all right, and we made it C plus D in equilibrium with A plus B, well, now A and B are on top as our products divided by C and D. What ends up happening to the value of K, it's 1 over it. All right, so here they actually write out the reaction backwards. So whatever you got for K for the initial reaction, if you were to completely flip it, the value of K would be the inverse, all right, which should make sense because you should always be writing K based on products divided by reactants for however the reaction is listed. All right, and if we change the reaction by multiplying by a factor, all right, whatever that factor may be, but stoichiometrically, it's going to be a part of every piece. So if we take the reaction A plus B forming C plus D, if we multiply everything by 2, then everything in the rate constant is going to be raised to the second power. So the value of K will be raised to the second power, the whole thing. All right, so if we were to take a reaction and multiply everything by 1/2, the value of K would now be K to the 1/2 power. All right, whatever factor we multiply the entire equilibrium by, we raise the K to that value. All right, and we've seen this in Unit 5. We've seen this in reaction rates. All right, if we substitute something, the Ks end up getting multiplied together. So if A plus B is in equilibrium with C, if C is in equilibrium with D plus E, we can substitute D and E for C, and we get A plus B in equilibrium with D and E. All right. So since we've substituted D and E where C was, we take these initial 2 K values, we multiply, and we get a new KEQ. All right. So we can add reactions essentially, and we just multiply the K values. So that's manipulating the rate constant. And it goes without saying, anything we do to the rate constant, we can also do to Q the reaction quotient. So if you were to change the reaction by multiplying everything by 2, if you were solving for the reactant quotient, all right, you would be raising that to the power of 2. Any type of manipulation that you can do to K, you can also do to Q. All right, now, why is it important to have the rate constant? All right, well, the concentrations or partial pressures of species at equilibrium can be predicted given the balanced reaction, initial concentrations, and the appropriate K value. All right, this is our ICE tables. So if we know what the concentration is of the reactant, and we know what the K value is for the reaction, we can figure out what type of change will take place, and we can solve for it. All right, so here's a simple one. An initial concentration, the products are both 0, minus X as the change to the reactants, plus X, plus X. This change step is based on the stoichiometry. All right, so you do have to be careful with that. And then the equilibrium, 0.15X, 0.15 minus X, X and X, we can set it up. All right, it would be X times X divided by 0.15 minus X. We can make those approximations. You will not have to solve the algebraic equation for, you don't have to solve the quadratic equation for any of these problems. All right, sometimes we can get some more complicated looking ones. All right, and again, we oftentimes find some kind of simplification to them. All right, whether we're taking the square root of both sides of the equation or if we're just making an approximation. All right, so we've also seen ICE tables where maybe we had to work backwards and solve for K, so they give us the values at equilibrium. So since we have this reaction of Fe3 plus thiocyanate forming FeNCS, it's a 1-to-1-to-1 ratio. So if at equilibrium, we went from having 0 amount of the product to 4.0 times 10 to the negative third, that change is going to be plus X, plus 4.0 times 10 to the negative third. So that means we would subtract that amount from both of the initial reactants, and that would give us our equilibrium concentrations. We can substitute those in and solve for K. And again, K is unitless, so you do not have to worry. All of the concentrations will be in molarity. All right. Particulate representations can be used to describe the relative numbers of reactant and product particles. All right. These diagrams, what you really want to hone in on is if you're given a reaction, you can almost see which one there's more of. So are there more HNO2s or more NO2s? If I look through the picture, I see there's more HNO2s. So the reaction is favoring that species. All right, we're not given the reaction here, but it would be HNO2 in equilibrium with H plus NO2 minus, and it would be favoring the HNO2, which is why we see more of them in the particle diagram. All right, here is another diagram. We have the 2 yellow plus the 2 green in equilibrium with the yellow green. All right, between the 2 temperatures, what we see happening is there are less of the reactants at the higher temperature. So if you're ever given an equilibrium system and you have a particle diagram, what they're asking you to do is just think qualitatively about the numbers of reactants, the numbers of products, all right, to get an idea, are there more products, which means a larger K, or are there less products, more reactants, which means a smaller K? All right, so you do have to look, the number of each type of particle will be represented very deliberately. So just that's what you're trying to analyze if you're ever given a particle diagram for an equilibrium. All right, now equilibrium and Le Chatelier's principle. All right, Le Chatelier's principle tells us how a system will respond when it has been stressed. And the way it goes is it tries to alleviate the stress. So let's say this is our teeter-totter, and we want it to move this space so that they were balanced. All right, we would need to move it to the right a little bit, so that, to the left, excuse me, so that this guy can push it down. All right, if you were taking physics, this would be like trying to balance a torque problem. I know a lot of you guys aren't in physics, but that's what would be going on. All right, so first off, we can see what would happen with temperature. Heating up an equilibrium or cooling it down is a stress. So In this example, we're given the reaction 2SO2 plus O2 in equilibrium with 2SO3 plus energy. Since we have the plus energy piece as a reactant, this tells us it's an exothermic reaction. All right. Now, the stress is the temperature has been decreased. So we can follow each line. The dotted line tells us that that's one moment in time when we've created this stress. The SO2 decreases its concentration, it plateaus, we're at a new equilibrium. All right, so SO2 has decreased. The O2 decreases, it plateaus, again, we're at a new equilibrium. The SO3, we see its concentration actually increase. So what's happening, the reaction is shifting to the right. We are making more of the product, SO3. We have less of the reactants, SO2 plus O2. I want you to think about something. Since we've decreased the temperature, it's like we've removed energy and the equilibrium has now responded to create more energy, almost to try to restore it. So what ends up happening if we're thinking of heat, we need to have an idea, is the reaction exothermic or endothermic? If it's exothermic, heat is a product. And if we remove heat, the reaction is going to try to make more heat. All right, what if we had added heat to this reaction? We would see it shift left. The SO2 and O2s would actually increase. The SO3 would decrease. All right, so that's something that would happen if we change the temperature. All right, now the concentrations. So let's say that carbon monoxide in this example was removed. All right, so we are removing one of the products. Let's see what happens in the CO. Again, it's shown in green. So what do we see happening to the CO2, which is our reactant? It looks like it's decreasing just slightly. The CO, the carbon monoxide, it has that sharp decrease, right, because it's being removed, but now we see it start to increase, and the O2 goes up just a little bit. If you remove a product, the reaction will shift right to make more products. All right, so that's what we're seeing in this graph. All right, we're getting less of the reactants because we're trying to make more of the products to make up for it. So if you remove a product, it will shift towards the products. If you remove a reactant, it'll go the opposite way. All right, and just going back to that, that's removing. If you add a reactant, the equilibrium will shift to make more products, right? Because it has more reactants to increase that rate. If you add a product, it'll shift in the opposite direction. All right, what about changing pressure? Changing pressure, we only worry about if it's a system that is a gas. So here we have N2O4 gas in equilibrium with 2NO2 gas. So changing the pressure, we're going to increase the pressure. Just keep in mind, pressure and volume have that inverse relationship. Increasing the pressure of a system usually goes with decreasing the volume, and vice versa. If you increase the volume, you would decrease the pressure. So in this example, though, we're increasing the pressure on the system. What we see is the NO2 decreases, the N2O4 increases. Why would that happen? If you increase the pressure, it's going to shift to the side of the reaction with less moles of gas. As a reactant, there's 1 mole of gas present. As a product, there are 2 moles of gas present. So if we increase the pressure, it's going to want to shift to the side with less moles of gas, almost to try to alleviate that pressure. So it's going to shift left to the N2O4, and we see that in the graph. All right. If we decreased the pressure by increasing the volume, we would have shifted right to make 2NO2. It would shift to the side with more moles of gas because it would almost try to fill up that space. All right, so here's our example. We have our gas equilibrium. The red represents the reactant. The gold is the product. And the red has more moles of gas, the 2. So if we get a smaller volume, it's going to want to clump up and make those B's, right, so that we can get less particles colliding with the walls. And if we increase the volume, which decreases the pressure, it's going to want to shift to the side with the red so that we can get more collisions to almost try to fill up that space. So that's what's happening with pressure. All right. And again, this is increasing the concentration. So they're increasing the PCl5. It's almost like it's being inserted. So once it increases, it starts to decrease as we increase the products. So this would be PCl5 forming PCl3 plus Cl2. So initially the reactants increase, but then they start to decrease while the products increase, right? Add a reactant, shift to make more products. All right, and again, the reason we're doing that is to get Q to equal K again. When we have that stress, Q and K no longer are equal, so we're no longer at equilibrium until that stress is alleviated. All right, so again, it's all about trying to get to a point where Q and K are equal to each other again. All right, and it can be used, so we will see in Unit 8 the addition of hydrogen a lot, pH, so certain reactions will happen at different pHs. We can apply Le Chatelier's principle to those as well, just by thinking if H is a reactant or a product at a higher pH, that actually means we'll have less H present, so it might shift one way. Right, so if we add the acid, we'll shift left. If we remove the acid, it'll shift right. Again, that stuff will all come up in Unit 8, so you don't have to worry about it for right now. But just know that Le Chatelier's principle will be used to describe more chemical situations in the future, right? Because we'll see more equilibriums. All right, and here is the summary. Pause on this slide. All right, couple important things to note. Increasing and decreasing the concentration does not change the value of K. Increasing and decreasing the pressure does not change the value of K. Increasing and decreasing the temperature does change the value of K. All right, the equilibrium rate constant is temperature dependent. All right, it's temperature dependent because it has to do with the rates of reactions being equal to each other, and the rates of reactions are based on the temperature. We've seen that in Unit 5. All right, something that's important, adding a catalyst has no change on a chemical equilibrium. Adding an inert gas will have no change on a chemical equilibrium. All right, adding something that's in the solid state or the liquid state that's not part of the equilibrium constant will not have an effect. It will not count as a stress. It will not change the equilibrium. All right. So now our salts have a certain solubility. The dissolution of a salt is a reversible process. It can be influenced by environmental factors such as pH or other dissolved ions. So we call these, we call the K value, the equilibrium constant, we call it the KSP, at the solubility product constant. So here we're looking at silver 1 sulfide. All right, silver 1 sulfide, you're probably thinking, okay, well, that's an insoluble salt. Well, yes, that's true, but it may be partially soluble. So we get an equilibrium where we get a little bit of the ions, but mostly it's solid. So it's an equilibrium situation occurring. All right, we have KSP values for all different substances. Typically, they're all measured at 25 degrees Celsius. All right, they would change based on the temperature, but we like to leave them at that same set standard temperature. All right, and what you'll notice just in this chart right now, they're all typically negative numbers. All right, which means now KSP, solubility product constant, it's an equilibrium constant. So if we're getting 10 to the negative 13, 10 to the negative 12, 10 to the negative 29, that means that they're the really small Ks, so they favor the reactants, which means the substance as a solid. All right, so how do we write these reactions? It is a solid dissociating into its ions. All right, something that's important to note, the subscripts of the anions become their coefficients. And when we go to write their KSPs, since it's products over reactant, there's no division here, right? Because it would all be over 1. You would never include the solids. and you're going to use the stoichiometric coefficients as your exponents. All right, so writing out KSPs should be pretty easy. We should feel good with these. All right, now A can be calculated from the KSPs. We still would make an ice table for these reactions. All right, now for a reaction like this, CuBr, right, copper 1 bromide, we're making one of each, so it would just be X and X. In some of our other reactions, so in here, the mercury 1 chloride, where the mercury 1 stays together, since its stoichiometric ratio is 1, its change would just be X, whereas there's 2 chlorides, so that's going to be 2X, right? So the change is still based on stoichiometry. So make sure you include those coefficients in front of your X. And so then if you were to write the KSP, it would be X times 2X squared from the 2. So you would get 4X to the third. All right, you're going to see the same type of KSPs coming about. All right, now if you're ever asked to calculate the molar solubility, all right, given the KSP, that means you're solving for X. All right, so X is the molar solubility of a salt, and it's always based on 1, because we always think of one salt dissociating into whatever respective ions. So you're always solving for X, even if you get the 2X, 3X, whatever it may be. So if you had 3X, that means the stoichiometric number was 3. That would be 3X raised to the power of 3, so 27X cubed. If it was 4X, it would be 4 raised to the power of 4, right? So it would kind of grow. But if you're solving for molar solubility, that is just X. All right? So you may see problems like this, where you are given the molar solubility and you're asked to go back and solve for the KSP. All right, so determine the KSP of PbBr2 if its molar solubility in water is 25 degrees Celsius is 1.05 times 10 to the negative 2. That is X, right? So we're going to get plus X plus 2X. We have the equilibrium values. We would substitute them in here. So the 2.1 times 10 to the negative 2 would have to get squared. You would multiply it. You would solve for a KSP. All right, so pretty straightforward problems. Stuff we've seen. Now, these solubility rules that we've learned about, right? So we know that like all nitrates are soluble. Their KSPs would all have very high values, all right? But the solubility rules line up with KSP values. So we know, for example, that iron hydroxide is insoluble, right? Most hydroxides are insoluble, and its KSP confirms that. All right, 4.87 times 10 to the negative 17th. We know that bromides are typically soluble except for the exceptions of lead, silver, and mercury. So lead 2 bromide, 4.67 times 10 to the negative 6th. Again, it's confirmed, so it matches up. Now, we saw the common ion effect. All right, so the common ion is an ion that's present from a salt, but it's coming from a different source. So in this example, we have lead chromate. All right. If we have lead chromate in a solution of chromate, example, sodium chromate, we're actually going to get less solubility, more solid. So the solubility of a salt is reduced when it is dissolved into a solution that already contains one of the ions present. So that common ion effect reduces the solubility. All right. How does it reduce it? Well, when you go and make those ice tables, instead of having 0 as the initial concentration of any of those ions, you have to put in the value coming from the common ion. So what is the molar solubility of AgBr in 0.001 molar NaBr? So the initial concentration of Br is not 0, it's 0.001. And whatever we add to it, it's negligible. So it just changes the complete calculation. You could see here, pure water, we're getting 8.8 times 10 to the negative 7th. In that solution of NaBr, we're getting 7.7 times 10 to the negative 10th. All right. It always reduces the solubility. All right, the common ion effect. Now, pH may be sensitive, all right, because the H may be a common ion. and it may do something to a reaction. So think about magnesium hydroxide. All right, magnesium hydroxide is only slightly soluble, all right? But if we had hydrogen present, hydronium ions, it's going to react with the OH. It's going to remove a product. Le Chatelier's principle is going to say you remove a product, we shift right. So the pH may increase the solubility, all right? If hydrogen ions are present, any basic insoluble salt will actually increase its solubility, all right, because we're going to be essentially removing product again and again. So the presence of a common ion decreases solubility, but insoluble bases dissolve better in acidic solutions. So that's pH less than 7. And insoluble acids actually dissolve in basic solutions. So those are pHs greater than 7. And again, we will touch on this again in Unit 8. All right, when we look at acids and bases, I just want you thinking when certain things dissolve, if they are basic or acidic, all right, one of their ions could potentially react with the environment around it, and that would remove it, and that would be a Le Chatelier, and that would cause a shift. All right, now free energy shows up at the end of Unit 7. Free energy is the whole point of Unit 9 of the AP Chemistry curriculum. So we will come back to this, so don't worry about it. The formula is pretty simple though. Delta G equals delta H minus T delta S. Enthalpy minus temperature times the entropy change. All right, there's a lot going on here. What ends up happening? When something dissolves, that's more random. So the entropy typically increases when we have a solid dissolve in the solution. All right, the breaking of the intermolecular attractions that hold the solid together, the reorganization of the solvent around the dissolved species, and the interaction of the dissolved species with the solvent all have enthalpy values associated with it. All right, but that can be really hard to predict. Sometimes it's exothermic, sometimes it's endothermic. They all have different enthalpies associated. So in going back to that formula, the delta G equaling delta H minus T delta S, it's really not a good way to solve for a chemical equilibrium because it's hard to tell if a system's going to have, if it's going to be endothermic or exothermic. The one thing, I'm going to mention it now, and we will revisit it in Unit 9, is that at equilibrium, delta G equals 0. So when Q equals K, the reaction quotient equals the equilibrium constant, the change in free energy is 0. And I want you to think about this image here. All right, in a chemical equilibrium, if we're thinking about a graph of free energy, it's going to look like a valley. And I want you to think of a ball. If the ball's over here, it's going to roll down. It's going to go past the equilibrium point and roll up a little bit, but it'll keep coming back down. All right, and eventually it'll stop at 0. All right, so the idea is that for an equilibrium reaction, if we go too far in either one direction, it's spontaneous to bring it back to equilibrium, right? So at equilibrium, delta G equals 0. Again, we will develop this more in Unit 9. All right, so that is a quick run through of Unit 7, chemical equilibrium. Certainly you want to practice being able to write the K for any reaction. You want to feel comfortable in predicting the shift based on Le Chatelier's principle. So you want to do a little bit of practice with that. All right. You want to be able to fill out an ice table and solve through, especially those solubilities. Those ice tables should be pretty easy. And again, that common ion effect, it is going to reduce the solubility of the salt. All right. So that should be a good review. Hope that helps.